I'm providing video support for assignment 94, the Bohr model. I will remind you, we had this model in class where you have a nucleus and then you have these predetermined energy levels, which can be thought of as orbits for electrons. So this is the fundamental picture for the Bohr model. Each of these orbits is a quantum state. So in this model, the innermost ring or orbit will be called n equal 1. The next one will be n equal 2. And there are an infinite number of these predefined energy levels within a hydrogen atom. Niels Bohr was the inventor of this model in 1913. And he used mathematics to calculate the energy of each of these quantum states. That can be expressed in this fairly simple equation here. E sub n will be the energy in joules of the quantum state n equal 1, n equal 2, etc. And it can be calculated using this equation, negative 1312 over n squared kilojoules per mole. In the note it says negative values for energy indicate that the electron is bound to the atom. That should make sense to you. These electrons are in some kind of well, and depending on where they are either at a lower or higher potential energy, but still at a negative value. Getting to 0 is freedom. And that would be ionization of the atom, escape from its well. So now I'm actually calculating the precise values for the energy levels 1 through 4. The way this works is you substitute values into this equation. And n is an integer, 1, 2, 3, 4, etc. And then you use your calculator. So the first energy level will be E sub 1, negative 1312 on the top. 1 is n, so square it, and you get 1 squared on the bottom. That I can do without a calculator as negative 1312 kJs per mole. That's the energy of quantum state number 1. I'll show you how to do E sub 2. That'll still be negative 1312. Now it's 2 for n. I have to square it. 2 squared on the bottom. And that I'll use my calculator. 1312 divided by 4, which is 2 squared. 328. So it's still a negative number. Still bound to the atom, but less tightly bound. It's in an outer ring now, and so it's negative 328 kJs per mole. So this quantum state is higher in potential energy, going up the well here. It's farther from the nucleus in the Bohr model, and this is how it's calculated. I'll ask you to try to calculate values for E sub 3, that is the energy of the third quantum state, and the fourth quantum state. Pause the video, check when you've got an answer. Here are my values for energy of the third quantum state, negative 146 kJs per mole, and the fourth quantum state, negative 82 kilojoules per mole. Here's my mathematics I used to calculate those. Here in part 2, it's just asking you to transfer your numbers onto this picture. So you can see the first orbit, second orbit, third orbit, which could correspond to shells in an atom. Energy levels are shells. And if we just transfer the numbers over, then this will have more mathematical meaning. So the first shell, negative 1312 kJs per mole. Second one is negative 328 kJs per mole. And third one is negative 146 kJs per mole. Number 3 is the same idea, except now we're looking at the picture in terms of an energy well, increasing energy as we go up to 0 kilojoules per mole at the top, which is freedom. So this will be the negative. This is the most tightly bound state there can be in hydrogen. The n=1 ground state, where the electron is in this first orbit here. And then the second orbit is significantly higher in energy. That's what this picture allows you to see, is that this is a big jump here between n=1 and n=2. And we'll see that that's very significant in terms of how hydrogen interacts with light. E3, -146, and E4, -82. So there would be an E5, E6, and you can see they'll get pretty close together here at the top. So here you see, continue on the next page. Use this as your notes to answer the questions that are on the next page and the page that follows. There you go.